welcome back to our video. So before we move forward to another dimensionless number, let me tell you um, something regarding the additional information, regarding the Prandtl number. Okay, so the Prandtl number, we say that it is actually a dimensionless number, and that is an intrinsic property of a fluid, which means its value is independent of the flow condition and flow geometry, right? So if we have gases have a Prandtl number equal to 1, it only means, or it only indicates that both the momentum and the heat dissipate through the fluid the momentum and the heat dissipates through the fluid at the same time. Okay? Since we say that, diba, the PR is the momentum transport and heat transport. Okay? Cp all over A is equal to mu Cp all over K. Okay, so we say that this is actually our PR, okay, the Prandtl number. And if this is equal to 1, then it only means this momentum and the heat dissipates through the fluid at the same time. That's why they are equal to 1. Okay, so for a fluid with a PR value that is way lesser than 1, what does it mean? If we have this what they call this correlation. If PR value, look at here, if we have a PR value way lesser than 1, then it only means that this heat transport is much larger than the momentum transport. So the heat diffuses very quickly. Heat diffuses very quickly, right? Okay. We have this large heat transport here. Okay. That's why if we have this kind of value of our PR, it only means that heat diffuses very quickly. But if we have a PR more much greater than 1, such as oils, the glycerine, and so on, it only means that the heat diffuses very slowly relative to momentum. Okay, relative to its momentum. Okay. Remember those values. Okay. Again, if we have Prandtl number way more than value of 1, then it only means that relative to its momentum, the heat diffuses slowly. Okay. And if we take a look at some values of the fluid regarding its value of the Prandtl number, say we have here liquid metals. The Prandtl number of this liquid metal is 0.04 to 0.04. Okay, the gases is about 0.7 to 1.0. The water is 1.7 to 13.7. The light organic fluids 5 to 50. What else? Say we have oils. The Prandtl number is 50 to 100,000, and glycerine is 2000 ranges from 2000 to 100,000. Okay, so if we take a look at this value of our Prandtl number, we can only tell the story behind this. That this, for example, these liquid metals, the heat diffuses very quickly relative to its momentum, unlike to the oils and glycerines that the PR value is much more way than 1, then the heat diffuses very slowly relative to the momentum of this oil and glycerin. Okay, so that is all about the Prandtl number. Okay, so next dimensionless number is what we call the Reynolds number. RE. Okay, the Reynolds number determines whether the flow condition is laminar, is in transition, or in turbulent flow condition. Okay, so the Reynolds number once again uses to determine only the flow condition if it is a laminar, transition. Transition means from laminar, it somewhere between the laminar and turbulent flow condition. Okay, so the Reynolds number is the ratio of the inertia force to the viscous force of the fluid. Okay, if we're gonna relate this, our RE is the inertia forces relative to the viscous force of the fluid. Okay, and we can also view this in relative to the property of the velocity, the upstream velocity, to the characteristic length of the geometry relative to the kinematic viscosity, V. Okay. Wherein our kinematic viscosity is what? Mu all over density. Okay. That's why we can say that our Reynolds number is equal to this, what I call this, the density, the upstream velocity of the fluid, then the characteristic length divided by the mu, or the dynamic viscosity, right? So we can have this whole relationship regarding the Reynolds number, and the resulting value can now dictates whether the flow is laminar, is in transition, or is it a turbulent flow. Okay. Okay, if we are gonna view this flow, laminar, the transition, and turbulent in terms of what you call this, in terms of illustration, and by the way, this is based from their experiments. Then they uses dye traces. They have the flow of water. They have this somewhat looks like this setup, that there is actually a flow here, fluid flow here, and they put some dye in the water and then observe the flow, what happens to the flow relative to the picture of the dye. Okay. So if the stream condition, we through their experiments, say we have this kind of Then the body put a dye here to view. So the dye will make a color in the water, and then they have this kind of image when the flow is in laminar condition. Okay, but if the flow became this much, then there's something started to disperse the dye here, then the flow views, it is now started to make a transition from laminar to turbulent. Okay, and then lastly, if we take a look at this turbulent condition, you can now see the disturbance of the dye in the water. Okay, it looks like this. So in picture, you can now see the different flows from laminar. It's smooth. The dye is looks smooth going through the streams of the water, and here comes the transition phase, wherein it is only between the laminar, and it will now transition to the turbulent flow. And if we're gonna take a look using their experiments on the picture of the turbulent flow, we can now view that the dye started to form like this picture. Okay, so the Reynolds number, through this through this Reynolds number, we can now determine if our flow is in laminar, in transition, or turbulent. Okay. Okay, so the Reynolds number at which the flow becomes turbulent, so the Reynolds number at which the flow became turbulent is called the critical Reynolds number. So the value of the critical Reynolds number is different for different geometries. Okay, so the critical Reynolds number differs with different geometries. Say we have this condition, and the given critical Reynolds number, or ECR critical, is this. If we have a flow over a flat plate, I mean flow over a flat plate, the critical Reynolds number is 5 times 10 to the 5 up to 3 times 10 to the 6. Okay, if we have a flow across a cylinder or sphere, our critical Reynolds number is 2 times 10 to the 5. Okay, and if we have a flow inside the circular duct, okay, our critical RE is 2300. Okay, so so beyond this critical Reynolds number, your flow is turbulent, is called turbulent. Okay, so always remember this condition and the critical Reynolds number, so that we can assess the flow of your fluid if it is at the laminar, or it became a turbulent one. Okay, so that's all for the Reynolds number, and we will now go to another dimensionless number, which is the Grashof number.